Hello! For this video, we are going to show whether the linear transformations defined by these two matrices are a one-to-one and onto linear transformation. And if satisfies both, we could also insert here the concept of isomorphism. Now, the first one is a 2 by 3 matrix and the second one is a 3 by 3 matrix. Here, we are going to show the linear transformation defined by these two matrices to be one-to-one or onto. In our first example here, it's just 2 by 2 matrix following m by n. The linear transformation defined here is r to the n to r to the m. In short, this is the linear transformation from r3 to r2. This is very important once we determine the important vectors such as 0 vector and a certain vector v that is to be used in determining one-to-one, and the concept of the domain as well and onto. On our second matrix, this is defined as again r to the n to r to the m. In short, this is r to the 3 to r3 linear transformation. Okay, so we will be using these concepts in our ideas that are laid with these linear transformations as we move further. In solving for a one-to-one linear transformation or determining a one-to-one linear transformation, we just need to show that the kernel of T of the specific matrix be equal to the 0 vector. Okay, that's also here. The kernel of T must be equal to the set containing a 0 vector. But what 0 vector are we looking for? This is where the purpose of this is very important. The 0 vector here is an element of our codomain. Here we have R2. In short, the 0 vector here must be 0, 0. On the other hand, we have here R3 as our codomain. So the 0 vector here is actually defined as a 0 vector in R3 as well. Aside from that, in solving for our kernel of T, we will need to satisfy this linear transformation, which is the product of A and a certain vector equal to the 0 vector. Same thing here, here. Okay, the 0 vector is already given in our first analysis using the linear transformation definition. But what v vector right now, this v vector and vector v here, these are elements of your domain R3. This is R3 as well. In short, your vector v is a vector comprises of v sub 1, v sub 2, and v sub 3 here as well. Your vector v is an element of your R3. Okay, so that is why again the definition is very important. And lastly, because kernel of T is an identification of your one-to-one linear transformation. Once you reach this idea here, then our linear transformation is a one-to-one. As for onto linear transformation, we need to identify the dimension of your domain. Okay, the domain here is this one here, R3. So the dimension here is 3. This here as well, the dimension of your domain is also indicated by this, so this is also 3. Okay, and in our onto, this dimension of domain should be equal to the dimension of your range. Okay, so your range later will be determined as this process will go on. So let's start with the determination of one-to-one linear transformation. Let's start with coming up with a reduced row echelon form of both matrices. Now, the reduced row echelon form is very important in determining not just one-to-one but also onto. Let's start with the one-to-one. 1, 1, 1, 0, 1, 1. So let's make here a reduced row echelon form. So this is already in a row echelon form. What we need to do is to make this 0, because the reduced row echelon form tells us that in a column containing leading one, such as this, the other entries would be 0. So that's correct for the first column. But for our second column, since this is our leading one, this should be 0. By the way, this and this are not leading ones, so you don't need to change them into zeros. We only need to change this. So by multiplying -1 to R2 plus R1 or row 1 to have a new row 1. So you have 0, 1, 1 here still. So negative of 0 is just 0, so this is still 1. Negative of 1 plus 1 is 0. Negative 1 plus 1, 0 here as well. So we have this in our reduced row echelon form. This will now be used in our definition here, where we pair it with a certain vector in this area. So we have here v sub 1, v sub 2, and v sub 3, and we are going to equate this to the 0 vector. Okay. Now this is defined as we are going to have here the product of a 2 by 3 to 3 by 1. So you're expecting to have a 2 by 1 matrix here. And with that, we are going to have this product here. The product you will have, okay, so your v sub 1 is 0. Sorry, let's not make this as a form of matrix. So you have v sub 1 equal to 0, and then, okay, your v sub 2 plus v sub 3 is equal to 0 as well. We have two variables, v sub 2 and v sub 3, for our what you call this one, the second equation. So that means we are going to let v sub 3 be equal to a certain arbitrary constant t, which means v sub 2 plus t equals 0. V sub 2 is negative of t. That would mean your vector here is expressed in this manner. You will have 0, you have negative t, and t. Okay? Or your kernel of t can be expressed as a set when you factor out t, 0, negative 1, and 1, such that t is an element of a real number. This is your kernel of t. Notice that our kernel of t doesn't contain the 0 vector alone. We have this vector and its multiples. This would mean that this is not a one-to-one linear transformation, because for this to become a one-to-one linear transformation, we need to show that the element of our kernel of t is just a 0 vector itself. This automatically means that our linear transformation defined by our first matrix here is also not an isomorphism, because an isomorphism is both a one-to-one and onto, and since it's no longer a one-to-one linear transformation, it should not also be an isomorphism. But of course, let us try to continue showing whether it's an onto or not, even if we are already sure that it's not a one-to-one nor an isomorphism. We are going to use the same, okay, this one here, the same reduced row echelon form. So you have here 1, that was 0, 0, 0, 0, then 0, 1, and 1. We see here our we have two columns. Okay, we have two columns with leading 1. This would mean that our basis for the range of t contains the initial two columns, the first and second column, the 1, 0, and 1, 1. So we have here 1, 0, and then 1, 1. In short, the dimension of the basis of the range of t is equal to 2, since there are two vectors here. Now looking back at our dimension of domain, which is a 3, okay? The dimension of our domain, which is 3, is not equal to the dimension of our range, because this is a 3 and it's not equal to 2. This means that this is also not onto, okay? Because it should only be onto linear transformation if the dimension of your domain is equal to the dimension of your range. And since our range here only contains 2, that's why it's no longer onto. So for our first example, it's not a one-to-one, it's not an onto linear transformation, and of course automatically it's not an isomorphism because it doesn't fit all the criteria. Take note that the dimension here of our kernel, I'm just going to insert this little concept, which is equal to the nullity of t is equal to 1, because it's actually the dimension of the basis of your kernel, and your base only contain 1. And of course, you are given here a certain concept that the dimension of your domain is just equal to the dimension of the basis of your kernel plus the dimension of the basis of your range. And 3, this is kernel earlier is 1, and you have here 2. It meets this criteria. So this is actually true to all. But of course, this is what we're looking for, and our kernel is just 1. So again, it's not a 1-to-1, it's not an on-to as well. So let's proceed to the second, and let's see if this is a 1-to-1 or this also established an on-to, and we could say it's an isomorphism. So again, we're going to come up with the reduced row echelon form of this 4, 0, 7, 5, 5, 1, 0, 0, and 2. The first one here is to come up with a leading 1. Let's make this 1 by multiplying 1/4 to row 1. Okay, so we'll have here 1, 0, that's 7/4, 5, 5, 1, 0, 0, and 2. Next, let's make this 0 by multiplying -5 to row 1 plus row 2 for a new row 2. We don't need to manipulate that because that's already 0. Okay, let's have some space here. Okay, so we'll have here 1, 0, 7/4. You have -5 times this is -5 plus 5, 0. -5 times 0 is just 0, is still 5. -5 times 7/4 is -35/4. Okay, and then you have here over 4, so that's -31/4. Again, let's do it again. -35 plus 4, that's correct. So 0, 0, 2. Okay, let's make this leading 1 by multiplying 1/5 to row 2. And since there are no other entries aside from this for our third row, let's also multiply 1/2 to row 3 so that it will become a leading 1 as well. 1, 0, 7/4, 0, 1, right? Then when you multiply this with 1/5, that's -31/20. Okay, and you have 0, 0, 1 here. So no need to worry about fractions. The next thing is to make this 0 and this 0 as well. So we're going to multiply +31/20 to row 3. That's 20. And add it to row 2 to make that 0. And also multiply -7/4 to row 3 plus row 1 for a new row 1. This is 0, 0, 1. That's 0, 1. And +31/20 plus this times that plus that 0. Okay, so 1, 0, -7/4 times 1, -7/4 times that 0 as well. This is now our reduced row echelon form for our second matrix. So multiplying that, solving for our kernel, we have here our v sub 1 because that's our vector, right, in R3, and our 0 vector in R3 as well. V sub 2 and V sub 3 is equal to 0, 0, 0. So we have V sub 1 be 0, V sub 2 0, V sub 3 is also 0. So our vector is also a 0 vector in R3. This means that the kernel of T is a set containing the 0 vector, and this is a 1-to-1 linear transformation. So we have established it to be a 1-to-1 linear transformation because we reached this point. Using the same reduced row echelon form, 1, 0, 0, 0, 1, 0, 0, 0, 1, we can see here 3 columns with leading 1s. In short, the basis for the range of T is the set containing the 3 columns or column space of our original vector 4, 5, 0. So we have 4, 5, 0. Sorry for that. 0. We have 0, 5, 0. And we have 7, 1, and 2. Let me check. 0, 5, 0, 7, 1, and 2. What does this tell us right now? The dimension of the basis of your range is equal to 3. Now looking back at our dimension of the domain here, it's also equal to 3. So for this case, for our second matrix, the dimension of the domain is equal to the dimension of your range. Here we have 3 equal to 3. In short, aside from this being one-to-one, this is also an onto linear transformation. With this being one-to-one onto at the same time, this is an isomorphism. Okay? So our linear transformation described or defined by the second matrix is an isomorphism. So this is what separates the other two, the two matrices earlier. It's not an isomorphism because it's neither one-to-one nor on-two. But even just one, even if it's on-two but it's not one-to-one, then it will not satisfy isomorphism. But our second matrix is both on-two and one-to-one. In short, this matrix or linear transformation defined by this matrix is an isomorphism. This will be the last video for onto and one-to-one linear transformations, including the concept of isomorphism. Thank you very much for watching.